today's lesson, we'll be discussing about exceptions to the octet rule or exceptions to the Lewis structures. Okay, so we will look at the first exception. The first exception is that the octet can only work for molecules with an even number of valence electrons. While this covers most cases, there are a few molecules that have an odd number of electrons. So let's look at an example here. Uh, Let's take nitrogen monoxide as our example. Nitrogen monoxide. There are 5 valence electrons in nitrogen and there are 6 valence electrons in oxygen, and together would be 11 valence electrons. Okay, now let's draw a skeleton structure. There you go. And we know that the least electronegative element would be the central atom for us. And in this case, nitrogen would be the central atom and oxygen would be the side atom. And we are going to place a bond between them. So now placing a bond, we have represented 2 valence electrons out of 11. We have used 2 and we are left with 9 more to be represented. We'll start placing these 9 electrons on the side atom first. That means on the oxygen. So there you go. We'll start with pairing them. 1, 2, 3, 4, 5, and 6. Now, if we look at oxygen, oxygen has that 8 electrons and would not be able to accommodate more than this. So we have used 6 electrons out of the 9 electrons and we are still left with 3 more valence electrons. And now we can place these 3 electrons on nitrogen. So we're going to place them like this as a pair, and then we're left with 1 more electron. So nitrogen does not achieve the octet. So let's look at the number of electrons that nitrogen has. 1, 2, 3, 4, 5. We can move a pair of electrons from oxygen to give more electrons to nitrogen. So let's move this pair to here. Okay, so can erase this. Okay. Now, nitrogen has 7 electrons 1, 2, 3, 4, 5, 6, 7, and oxygen has 8. Again, remember that we can move these pair of electrons also to form a triple bond, but that would give nitrogen 9 electrons, and nitrogen cannot accommodate more than 8 electrons. So, we cannot take this lone pair of electrons and move here. So this is the final structure for nitrogen monoxide, where this nitrogen here is not able to achieve its octet, and the reason is because it has this odd number of valence electrons, and that's an exception. Okay, now the second exception that we're going to look at is the compounds that are formed with boron and beryllium. And we're going to start with this compound, boron trifluoride. Okay, so we know that fluorine would be the side atom, so boron would be the central atom, and fluorines would be on the side. Okay, let's calculate the total number of valence electrons. Boron has 3 valence electrons, and there are 3 fluorines, and each fluorine has 7 valence electrons. So together, this structure has 24 valence electrons. Okay, so we'll start with placing 2 valence electrons with boron and each fluorine and form a single bond. There you go. Okay, so we have used 6 valence electrons out of 24. We have used 6 and we are left with 18 more valence electrons to be represented in this molecule. And we'll start placing these 18 electrons on the side atoms first. So we'll start with this fluorine. Again, you can start anywhere. You can start with this fluorine or this fluorine or this fluorine. It does not matter. Okay, so we'll start with this one. 1, 2, 3, 4, 5, and 6. This fluorine has achieved its octet now, and we move on to the next fluorine. 7, 8, 9, 10, 11, 12. This fluorine also has achieved its octet, and we're going to move on to this fluorine now. 13, 14, 15, 16, 17, and 18. So we have used all 18 electrons and we are left with 0 valence electrons, and all valence electrons are represented here. And now we know that fluorine is a side atom, would not form a double bond, and boron would only have 6 valence electrons right now. Okay? And that it can only form 3 bonds and would have less than an octet. Less than an octet. So it has only 6 electrons in its structure, and that is an exception to boron. Let's look at beryllium fluoride as our next example. So we have calculated the total number of valence electrons, and this compound has 16 valence electrons, and we need to represent all 16 in our lowest dot structure. So the first step would be to draw a bond between beryllium and the 2 side atoms, and that would be each bond represents 2 electrons, so that would be 4 valence electrons, and we are left with 12 more to be represented in this structure. We're going to start with the side atoms first. You can start here or here, it does not matter. Either one of the fluorines is fine. Okay, so we're going to place the remaining 12 electrons. So that would be 6. This fluorine has 8 valence electrons now, and so therefore we need to move on to this fluorine. And there you go. We have represented all 12 of them. So fluorine has 8 and beryllium has 4 electrons represented by these 2 bonds. So because of the structure of beryllium, it's a very small atom, it would form a covalent bond and would only have 2 bonds like these and would never be able to achieve that octet. Okay, so that is an exception. The last exception that we are going to discuss is that third row elements are lower in the periodic table may exceed the octet row. So let's look at the periodic table. And this is third row or period 3. And we have phosphorus, sulfur, and chlorine. So elements which are in third row and down, that means period 3, 4, 5, 6, and 7, these the elements in these periods may exceed the octet rule when placed as a central atom. Okay, so we will always try to satisfy the octet rule first, and then if we have electrons that are left over, we'll place these excess electrons on the central atom. And the reason we are able to place these excess electrons in the central atom is because from period 3 and down, we have this orbital, which is a d orbital. Now, the central atom is able to accommodate these extra or excess electrons in the d orbital. Okay, so we are going to start with one simplest example, which is phosphorus pentachloride. Okay, phosphorus is in group 5A and would have 5 valence electrons, and chlorine, there are 5 of them and there are 7 valence electrons in each. So together this has 40 valence electrons. Okay, we know that phosphorus would be the central atom, as the least electronegative atom would be the central atom, and phosphorus being the least electronegative in this molecule. So we'll place phosphorus in the center, and we are going to place the 5 chlorines on the side. So 1, 2, 3, 4, and 5. And we're going to draw a bond between each one of them like this. Each line represents 2 valence electrons. So out of 40 valence electrons, we have used 10 and we are still left with 30 more to be used or being represented in this structure. Always remember we'll start with the side atoms first or the outer atoms first, and we are going to place the electrons on chlorine. 1, 2, 3, 4, 5, 6. Now we can move on to the next one because this chlorine will not accommodate more than that. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So we have represented all 30 of them. And this here is a Lewis dot structure for phosphorus pentachloride. And if we look at the central atom has more than 8 electrons. It has 10 electrons now, and the reason phosphorus is able to accommodate more than 8 is because of the d orbital. It has a d orbital and we can dump the extra electrons in the d orbital.
Let's look at a different example now. We have this polyatomic ion XeF3 with a positive 1 charge. The total number of valence electrons would be 28, and this would be our skeleton structure. And we have placed a single bond between each fluorine and the xenon atom. And by placing that bond, we have used 6 valence electrons, and now we are left with 22 valence electrons. We are to place these 22 valence electrons on each on the side atoms first. So we'll start with on one of the fluorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. I have used 18 electrons, and we are still left with 4 more valence electrons to be represented. And this is where we can use these 4 electrons and place it on the central atom as lone pairs. Okay, so if you look at xenon has these 4 electrons, and then 5, 6, 7, 8, 9, 10. It's able to accommodate more than 8. It can exceed the octet rule, and the reason is that xenon is in period 5, and anything in period 3 and down can accommodate more than 8 electrons. Exceeding the octet rule.
So the last thing to add would be that if we are drawing Lewis structures for polyatomic ions like this one here, we need to represent the Lewis structure in these brackets, and then outside the brackets we need to represent the charge of the polyatomic ion, and in this case it is +1.